Hello everyone, my name is Connor Smiley, and in this video I'll be going over my speed-controlled spline following tech demo. So we can see we've got this lovely van looping along this spline at a constant rate. So this is a Catmull-Rom spline formed by these four black spheres right here. So 4 is the minimum amount of points we need to form said spline, and in between this spline you can see a bunch of intermediate points. So these are the sample points being used to create our speed table, because as you can see, there's different distances between the sample points. We can see towards the middle there's a longer distance, but as we move close to the black spheres, the distance narrows. So what we need to do is we need to build a lookup table that maps distances to interpolation values such that the change in interpolation is uniform given varying distances, resulting in constant movement speeds. So let's dive into the code. So once again, we're in my engine using the DirectX toolkit as a renderer. It's super duper cool. I have this spline object, just using a very procedural paradigm where I've just got a bunch of data and methods that operate on the data. So as I said, the speed control table is composed of these sample points, which simply map distance to a uniform interpolation. So I have this speed table type, which is a nested vector. So the outer layer is going to be equal to the amount of points in the spline. So the size of this point structure here is going to be the outer layer. And then between 2 points, we're going to have an inner vector containing a bunch of sample points. So a spline is composed of both points, which is just a list of 3D positions, a speed table, and then we need to store the current point we're moving towards. We need to store the index of the current sample, and we need to store the distance along our spline so far as well. I've got a couple helper functions that just give the for control and endpoints given an index and a bunch of points within a spline, just automatically does modulus and writes the output to me. And then I take that function and I've just lifted it into a higher order function that will interpolate along a Catmull-Rom spline. The DirectX simple math library is super cool. It comes equipped with a Catmull-Rom evaluation function, which is vectorized, so it's going to load a bunch of floating points into vector registers, then do this simd Catmull-Rom function. So my preprocessor doesn't seem to be working right now. This should be defined and we should be seeing this, but yeah, it looks like Microsoft can't get their IDE working, so we'll ignore that. Or Control Shift, and looks like I can't even use Microsoft's IDE. Sorry about that. Okay, but yeah, cool function. And we've got our speed control table, which is the most complicated thing in this entire program, and it's honestly not too bad. Basically, we need to calculate the arc length between 2 points on a spline, and then using those, we map distances to interpolation. So the way we do that is given a certain amount of samples, so the greater this number is, the more precise our speed control table will be at the cost of computational and memory complexity. But once we've established an appropriate amount of samples, we just subdivide evenly for all of our samples, and we summate the arc length by sampling our Catmull at the previous position, and we subtract it from our current position, and we just take the length of that line, and then given that interpolation value, add the distance so far along the spline to that sample. So once we've got, again, that speed table, we pass in a spline object, and we can remap that to an appropriate t value. So we take a current and a next sample point along our spline. So the outer layer, which is the point, so which of the four black spheres we're between, and then which sample we're currently between. So our current sample and the sample ahead of us, again, just bounding that, so no array access issues. And we lerp between the sample point's current and next t value because that's what we want. But it's kind of like uh, a hierarchical lerp where we're returning t values and we're using distance to determine the initial t value. So what we do is we take the current distance along the spline subtracted by the distance of the starting sample point, and we divide that by the total distance in between our current and next sample point. So that's guaranteed to give us a value between 0 and 1, which we can sample t values with accordingly. So once we have all of that, we can update our point and sample indices by looping until the distance along our spline has exceeded the arc length of our current interval. So if that happens, we simply increment our point and we reset the samples. So all that's doing is saying, hey, once we go from here to here, we need to start going from here to here and vice versa. So yeah, that's pretty much it. The only thing I haven't gone over is the following code itself, which is follow path. So we can see that we're given a time delta and a speed right here, or linear velocity as I labeled it. And all we're doing is we're just incrementing distance at a constant rate based on time. But not only do we need to perform a translation, we need to perform a rotation as well. So we do that by taking the current and the future position of our van moving along the spline. So now that we have two positions, we can subtract them and get the normalized difference, which we can use as a direction vector to plug into the Frenet frame algorithm, which effectively orientates an object using the cross product. So we have a forward vector, we know our world up vector, which we can use to get our right vector, and then cross those to get the above vector, which allows us to input the columns of a rotation matrix, and from that point we are good to go. And with a little luck, we're left with a little something like this. So once again, we can see our van translating and being oriented nice and smoothly at a constant rate. So once again, thank you very much for listening.